Okay, now I'm on the YouTube live stream. So let's talk about ADC. Let's see how can we use ADC. Oops. How come I can hear my own voice? That's weird. Okay, now I think we're good. Oh, I need to mute yourself, otherwise I can hear whatever is on your speaker. Okay, now I'm good. Right. So if we have an ADC that has 3-bit, and this is, let's see, this is given condition, and we know this ADC can output maximum voltage. ADC maximum that can take maximum voltage that equals to 1.5 volt, and the minimum voltage it can take, it's -2. That's a range of ADC voltage, depends on the chip you have. And so those informations are really depends on the ADC, the chip itself, right? You couldn't really do anything about this. This is kind of the equipment you have. Then if we have a input voltage, V in, that's the voltage, analog voltage you can measure. That equals 0.2 volt, 1.2 volt. Now the question is, how can we find the code, the binary code or the integer code of this corresponding input? Of V in. So we need to find the code, the binary code for the V in, because we know analog ADC. Do you guys have any questions? I hear someone is talking. Any questions, guys? If you don't have questions, give me a thumbs up on YouTube. Okay, I think we're good here. Alright, then I want you to think about this practice. How can we convert this 1.2 volt into a binary code? Because what ADC does is it converts any analog voltage. Whose speaker is on? So I need to make sure. So this should be your analog input. Can be any type of voltage signal. In this case, we only give you one voltage signal at one particular time. Let's, for example, at this T, and that voltage here is 1.2 volt. I want you to convert that into a digital signal, digital number. Remember, if we have 3-bit, so this ADC only has 3-bit, so it can only give you something between 0, 0, 0 all the way to 1, 1, 1. So the task here is to convert this 1.2 volt into a 3-bit binary code. So the way to do it is solution gonna be, the first step is you need to find out what's the quantization for this ADC. So that's Q, and the quantization equals the maximum ADC voltage minus the minimum ADC voltage. over the 2n minus 1. N it's a bit here. So in this case, you can plug in all the numbers. Maximum ADC voltage equals 1.5 volt. The minimum ADC voltage is negative 2 volt. And divided by 2 to the 3 minus 1. Then you're able to find out what is Q quantization. This is kind of a resolution of the voltage. So if you do the calculation, you realize that equals to 3 point, oops, increase this, 3.5 divided by 0.5. Oh, sorry, divided by 7. That will give you 0.5 volt. So that's kind of the resolution of small steps of voltage this ADC can detect. Then once you have this, the Q quantization, and you're able to find the code. So the code, the corresponding binary code equals, you take a round, V in, that's the analog voltage input, minus VADC minimum, and divided by Q. And this is equation to find out what's the corresponding Q, the code for any given voltage input. And you can plug in all the numbers. This should be round. Plug in numbers, you get 1.2, that's the input voltage, minus the minimum voltage, which is negative 2 volt. Missing the volt here. Minus 2 volt, that's negative 2. So make sure you have a negative sign there. Divided by Q, which is 0.5 volt. And if you do the calculation right, you will end up with an integer number 6. That's the decimal number. You can convert that into a binary number, which is 3-digit binary number. You can ask yourself, quiz yourself, what's the corresponding binary number for that? Okay, I will pause here. Can someone tell me what's a binary number for 6? Use 3-bit binary code. Leave me a comments on YouTube. Yes, thank you, Aaron. That's 110. Let's leave it. That's the binary code. Yes. Now you have this. So the corresponding V in equals 1.2 volt. All through ADC, you convert that to a binary code, which is 110. It's not too bad, right? But let's go back here. This is just one single sample point along all the informations, right? If I give you a curve of analog voltage signal and along the time axis, are you able to kind of tell me what are the corresponding 3-bit binary words to those inputs? I think you are able to do it as long as you find the next sample point. For example, maybe the next sample point T2 is here, and you have a different voltage V in, then you do the same thing, find the V corresponding binary code for this V in. And then you are able to plot both analog and digital voltage signal. Okay, so that's a practice to, if you know what's the input and you can convert that input analog signal to a binary 3-bit code. Now let's look at another practice, which is kind of the same idea, but now we only know the code. I want you to find out what is the input analog voltage. So let's give, so now the given here is a 3-bit ADC, and now we have VADC maximum equals 5.25 volt, and VADC minimum equals to 0 volt. This is a different type of ADC. Has the same 3 bits, but the maximum and the minimum voltage is different. Now, instead of knowing V in, now we know the code. We know code equals 2. It's a decimal number 2. And we need to find out what is the V in, estimated V in. We add a hat, so it's V in hat. Tell ourselves this is the estimated analog voltage signal. So I want to ask you why here's the estimated analog signal. Can we just find out what's the input voltage signal by using that code? On pause here, I want you to let you to think why here we call it estimated. If you know the answer, you can unmute yourself and shout out the answer through Zoom, or you can just type it on YouTube. Do anybody know the answer? Why it's called estimated? Okay, seems no one knows the answer. Okay, I can tell you why. Because do you remember the word I mentioned? Lost. Loss of information. The ADC and DAC, they do the data conversions, right? But during the ADC, there's loss of information, and this is irreversible. So once you convert the analog signal into digital signal, you already lost a lot of information there. That's why when we only know the digital code of the signal, we can only estimate the input voltage signal based on the given information. We can never get the exact accuracy value for that input voltage signal. Okay, that's why it's called estimated V in hat. Okay, let's move on to solution. How do we find the estimated voltage signal? So first step, it's the same, need to find what is the quantization resolution is. So Q equals VADC maximum minus VADC minimum divided by 2 to the n minus 1. This is the same, 5.25 minus 0 divided by 7. Okay. And we find this is about 0.75 volt. So that's kind of tell you the resolution of the voltage step. Then the second step can find out the estimated analog signal Vn by using the code, the given code, times Q, that's a quantization resolution, plus V offset, plus minus Q over 2. That's kind of the tolerance someone mentioned there. Now, if you plug in everything, we know the code, which is 2. You don't need to convert that into binary because everything else there's no other binary code number here. Just copy 2 from there times Q equals 0.75 volt plus the offset voltage here. It's the minimum voltage, ADC minimum. So in this case, it's 0 volt here. Plus 0 plus minus Q over 2, that is 0.75 over 2. And this is equal to 1.5 volt plus minus 0.375 volt. So now you can say if you know the digital code after DAC output, you were only able to find out a range of voltage that corresponding to that code. So you don't really know exact value, but you know that input voltage is in between this range. You can map this around, just hopefully you remember that map. So remember, we can have a map if we have voltage start from 0 to let's see, what's the voltage here? Let's see, for example, 5.25, and this is a binary 3 bits, so you can divide this by 2, 3, 4, 5, 6, 7, 8, and each interval represents a binary code, right? 000, 001, and all the way to 111. So what you get here is, you know the code is 2, so, and for example, this is 0, 1, 2, 2 is 0, 1, 0, and this is 2. The corresponding binary code is 0, 1, 0, and that only tells you here is 1.5 volt, and right here is 1.5 minus 0.375, and at here it's 1.5 plus 0.375 volt. So it only tells you this range. That's where your analog signal will be located. But we do lost the information of the accurate value of the analog voltage signal. Hopefully I explained that through. If you think you understand this, give me a thumbs up so I can move on. And by the way, and you would probably need to remember the process equation, how we did this. So first, find Q by using this equation, V ADC max minus V ADC minimum over 2 to the n minus 1. Then, in order to find a code, you need to use this equation. Take a round number of V in minus V minimum over Q. That's how you convert analog to digital. In the second example, the first step is the same. Find the Q first. Then after you have the Q, the estimated voltage signal equals Q, the code times code times Q plus V offset plus minus Q over 2. That will help you to identify a range of the input voltage signal. And these two methods, the equation we use here to convert digital to analog, and this is called positive coding. Okay, there are also another way is called negative and positive coding, and we don't need to know that, but just know there's other different type of coding. This is just one of them. And so, like I mentioned, we will talk about, we have a coming exam later next week. So if we have something, I give you a sequence of signal. For example, here, I give you a sequence of V in. I tell you each sample point, 0. Yeah. For example, each second it's a sample point, all the way to t, a second. And on the vertical axis, those are the voltage from 1, 2, 3, all the way to maybe 10. If I give you all the voltage values at each sample point, are you able to convert this to a digital voltage? Or way out. The digital output is going to be either high or 1, right? So 1 and 0. And this is also time. So are you able to, by using the given analog voltage at each time step, to find the corresponding 3-bit binary code? That's a question you need to ask yourself, and because it probably would have a big possibility on the exam. Just saying. Okay, that was a quick review on what we learned on ADC. Oh, by the way, just one another thing is, now I give you this analog voltage sampling, and you need to find what's the corresponding digital output. Also, I can give you a sequence of digital output and let you to find what is the estimated voltage analog signal. Okay, so we're done with reviewing this. Now we're gonna go back to Zoom and stop the live stream here.